Chapter 45, Applications of Nuclear Physics. We're going to focus in this chapter on primarily the application of nuclear energy. That is, how do we extract energy from the atomic nucleus? And there are two major aspects of this application. One is a peaceful way of doing that, and that is to build a nuclear power plant. And another is for military application, that is nuclear weapons. We're going to look at the physics of both aspects of applications. Both have to do with, of course, nuclear energy. And the key idea behind harnessing energy from the atomic nucleus is this diagram we saw in the previous chapter. This is binding energy per nucleon as a plot of the atomic mass number A. You can see here the most stable nuclides are the intermediate ones, such as iron. Heavier ones and lighter ones are not as stable. So if we can take the heavier ones and split them apart, or take the lighter one and fuse them together to reach more stable intermediate sized particles, we can then lower the energy of the resultant particles to a lower value, and therefore releasing this excessive energy, and that is the energy that we can harness from the atomic nucleus. So here we split the atoms. Here we fuse the atoms together. This is called fission. This is called fusion, as we know. Fission is we can apply fission to build atomic bombs or nuclear power plants, which are the type of power plants in use today, fission type. And fusion, the only practical application, the practical device that we made out of fusion is unfortunately a bomb. It's a hydrogen bomb. And on the other hand, we also want to see if there's a way for us to build a power plant based on fusion. This turns out to be far more difficult than fission. We'll see why that's the case. But we're still working very hard on that, because after all, many scientists believe that this is the energy source of the future. So now let's take an overview of the physics of fission. The large nuclides above uranium-92, in nature, they're all radioactive, which means they are not stable by themselves. They will split into other particles, but it's a natural process that can take a long time. For example, uranium. Uranium has a typical half-life of in the billions of years, and this is a process that eventually happen by itself, but we're not going to wait that long. In order to get extra energy from fission, we do not just wait for the uranium to decay naturally. Rather, we use a neutron to bombard a uranium or any other heavy nuclides for that matter, to induce the splitting of this large nucleus into smaller pieces, therefore releasing energy. This is called fission. So it's neutron-induced splitting of heavy nuclei, such as uranium, plutonium, thorium, and so on. Here is the generic formula for such a fission process. This is neutron, and this is the target nuclide, such as uranium, plutonium, and the neutron is captured by this target particle, and you can see A becomes A plus 1, Z remains Z. We put a star here to indicate this is what? An excited state. Okay, it becomes very unstable, and it decays by emitting a gamma ray to go back to the ground state, and then this guy, having one extra neutron, becomes less stable than before, so it decays into two particles, Y and Z. These are intermediate sized particles, and very importantly, in the same process, it also releases a few neutrons. I used the letter K to indicate the number of neutrons emitted. That K can be 1, can be 2, can be 3, and so on, depending on the particular Y and Z. So you can have actually different types of ways to split into these two constituent particles and resulting particles. And here, in fact, is a diagram that people found for the percent yield, of fission yield, or the probability of finding the yield particles to have this much atomic mass number. Okay, so what we're plotting here is this is the so-called fission yield, the probability or percentage. That is, what kind of percent of the fission yield will have this kind of atomic weight or atomic mass. So we're plotting either AY or AZ. Okay, AY or AZ. That's what we're plotting. Using uranium-235 as an example. So X is uranium-235. Here is the actual decay formula, the fission formula for uranium-235. 235 captures a neutron, and it turns into 236 at excited state. Then it de-excites, producing a split into two parts, Y and Z, plus a number of neutrons. And this Y and Z may have a certain atomic mass number, and it varies. So here, this is the probability distribution. You see, this is a totally symmetrical curve about the middle. The middle is roughly 235 over 2. Now, it's not an even number, so we cannot actually split into integers. But roughly speaking, this is a case where the yield particle Y or Z, they have roughly equal mass. Okay, roughly equal mass. So it's like 118 and 117, roughly equal mass. And this probability is not very high compared with the case where you have a slightly heavier particle Y and a slightly lighter particle Z, or a slightly heavier particle Z and a slightly lighter particle Y. This curve is symmetrical about the middle, and that is not a surprise at all. This is actually, it's a trivial matter why this curve is symmetrical about the middle, because what we're plotting is AY. For example, we're plotting AY. So what's about AZ? AZ is predetermined because AY plus AZ equals AX. That's the conservation of atomic mass number. Okay? Well, at least roughly. I mean, there's a 1 here. It doesn't really matter that much. So basically, the sum of these two atomic mass numbers are pretty much a constant. And then what we have here, for example, this is 145 and 90. Okay, so the first particle whose atomic mass number is being plotted is Y, and its atomic mass number is 145. And as a result, the next one should be 90. Okay, should be 90, or in fact 91 if you consider that, 91. Now, if you go that way, you find that there's another point here where the first particle has 91 and the second particle has 145. Now, it doesn't really matter which one we call first particle, which one we call second particle. So clearly, these two events are really the same event, isn't it? Right? You produce two particles with 145 and 91 atomic mass numbers, respectively. Here, produce two particles with atomic mass numbers 91 and 145, respectively. These are the two same events. Of course, the chance of happening the same. Okay, so that's why the curve is symmetrical. So what that does tell us, the shape of this curve, it does tell us that the most likely event is when you split into something into two pieces. One of them has about like 140-ish. The other one has about 80-something-ish. Now, neither of these two particles are stable, so they continue to split even further. So it's a reaction that has many steps. Eventually, it will go down to more stable particles. Now, what is the most important feature of this fission process? It is induced by a neutron, and the process also produces more than one neutrons. This is the most important aspect. I highlight this term neutron. Why is that? Because those neutrons, in theory, can be used to trigger even more fission process. Okay, those neutrons can go on to trigger even more. So this reaction, when started, in theory, can go on and on and on, because one neutron, which starts the process, splits into, produces k neutrons, k greater than 1, and these k neutrons that can go on to produce more splitting and more splitting and splitting, and the process can go up exponentially. This is called a chain reaction. A chain reaction. Now, the letter K denotes the number of neutrons produced in this process. And again, this K varies depending on what Y is, what Z is. But for uranium-235, if you average all kinds of possibilities for Y and Z, there are a few dozen of them, and you find that on average, K is about 2.5. On average. Okay? 2.5. Now, this is what we call K. It's different from what we call K effective. What's K effective? K effective is the effective number of neutrons that can actually go on to the next stage, causing another splitting in the next step. The reason why K effective is not equal to K, in fact, is less than K, is because some of these neutrons, after they got produced, they escape. Okay, they move very fast with a typical energy of a few MeV. They travel extremely fast, so they just escape the region, and yet some others would simply scatter off a target nuclide in an elastic scattering without being captured to produce this reaction. Rather, they just scrape by and they just move on to other places. So not all of these 2.5 neutrons on average will go on to the next stage. Out of these 2.5, only this number, K effective number of neutrons, go on to the next stage. Now, the number K effective is extremely important. If K effective is greater than 1, then on average, each neutron will produce more than one neutron that will go on to the next stage, let's say 1.5. And that 1.5 neutrons will go on to the next stage, and each of these neutrons will produce another 1.5 neutrons. So you see, it's 1.5 to the power n after n steps, right? And these things happen very fast. Okay, they happen very, very fast. We're talking about microseconds for many, many steps of chain reaction. So therefore, as long as K effective is greater than 1, you can have a runaway reaction. That is what leads to an atomic bomb. Okay, if K is equal to 1, then we say it's sustained chain reaction, which means one neutron come in, effective one neutron come out to go to the next step, and that neutron produces yet another useful neutron, another one, another one. So the reaction will proceed at an even pace. That's called sustained chain reaction. That is what we want in a power plant, a nuclear power plant. If K effective less than 1, then the reaction will not sustain by itself, it will be diminishing. So you have one neutron. After that, less than one neutron is produced, which will be useful for the next stage, and so on. So the reaction certainly cannot sustain. It's gonna diminish by itself. So again, if you want to build a power plant, that's what you want. K effective equal to 1. And if K effective deviates from 1, we must quickly act to control the value so that it remains close enough to 1. A runaway reaction is what's desirable for building a bomb. So we're going to look at the physics behind both of these applications. The typical energy involved or released in this process, when uranium undergoes fission, is about 1 MeV per nucleon. For typical uranium splitting, again, it depends on what Y is, what Z is, but on average, we're talking about 200 MeV of energy released. Now, this guy has 235 nucleons, so roughly speaking, it's about 1 MeV per nucleon. That's energy released. If you compare that with the rest energy of the uranium, or of each nucleon has rest energy. We're talking about the energy of the proton, the rest energy of the proton and neutron. They are 938 and 939 respectively. So roughly speaking, they're about 1,000 MeV of rest energy, and of which 1 MeV is converted into energy. So the mass loss as a result of the fission is about 0.1%, or 1 in 1,000. So again, 0.1% of the mass of these uranium nuclei are actually turned into pure energy. Even though it's only 0.1%, that's a huge amount, because we're talking about m times c squared if you convert all this lost mass into energy. If you compare that with a typical chemical reaction, okay, in a chemical reaction, what kind of mass difference are we talking about? Well, in a typical chemical reaction, we're talking about a few EVs per molecule in a chemical reaction. But you compare that with the rest energy of the molecule, even the rest energy of a proton, which is the smallest of the nucleus, and that's 1,000, about 1,000 MeV, right? Compared with 1 EV, you look at that. We're talking about energy, a mass ratio of about 1 in a billion or less. Here, there's 1 in 1,000. That's not bad at all. So therefore, the mass ratio difference is between 1 in 1,000 and 1 in a billion. That is 6 orders of magnitude different. And therefore, we say a typical nuclear reaction through fission releases about 1 million times the energy in a typical chemical reaction. Again, 1 million times the energy of a typical chemical reaction. That's the power of nuclear energy. So this is a good number to know. Okay, 1,000 of the rest energy converted. And Here is a numerical example. 1 kilogram of uranium-235 undergoing fission completely, it's completely converted into energy. That's going to produce this much kilowatt hour, okay, 23.7 million kilowatt hours, or 20,000 tons of TNT yield. TNT is a type of high explosive, which whose yield equivalent we'll talk about in a minute. So 1 kilogram uranium-35 is equivalent to this much, 20,000 tons of conventional explosive. So that's the basic physics behind fission, and then depending on what you need, what you want, you can use that to build a bomb, or you can also use that to build nuclear power plants. And from a physics point of view, the physics of both applications are of interest, and therefore we're going to start with the discussion of how the nuclear fission bomb works, and then we're going to also discuss the how nuclear power plant operates, and we'll also deal with the issue of nuclear safety.